Let's move on to Geometry, Lesson 8.3, Arc Measure and Length. We have some definitions. An arc is a curve that is a subset of a circle. Arc measure is the measure of a central angle intercepting the arc. A degree is 1/360th of a circle, and a circle is 360 degrees. A few more definitions. We have the diameter. Diameter is a straight angle dividing the circle into two semicircles that have arcs measuring 180. In this instance, we have diameter YW, and you have semicircle YW, following the way that I'm moving the cursor. And on the other side, you would have semicircle WY, following the cursor. A minor arc has a measure of less than 180 degrees. So in this circle, one of the minor arcs would be WX, which is 60 degrees, less than 180. A major arc has a measure more than 180 degrees, and as an example of a major arc in this circle, we could say arc YWX. Minor arcs are always labeled with 2 points. Major arcs are always labeled with 3. A major arc's measure is 360 degrees less the measure of the minor arc with the same endpoints, and we'll be proving that right now. So in circle V, we have the measure of arc WX, which is 60 degrees, which is a minor arc, and we have the measure of arc WZX. So let me go ahead and erase this part, and we'll highlight what we need for this explanation. So the measure of arc WZX, which is our major arc, will be 360 minus 60 degrees, which is 300 degrees. XY and YZ are adjacent arcs. So XY and YZ are adjacent arcs. They're next to each other. They share point Y in common. The measure of an arc formed by the union of two adjacent arcs is the sum of the measures of the two adjacent arcs. This is postulate 8.3.1. This should sound familiar. We've had angle addition postulates, segment addition postulates, and so forth. So the measure of XY plus the measure of YZ, both of those arcs, equals the measure of arc XZ. So once again, the measure of arc XY plus YZ equals the total arc XZ. Example 1. Let's find the measure of each arc in circle V if the measure of YZ equals 45 degrees and the measure of WVX equals 60. The first thing I did for this drawing was I drew in the given of 45 degrees, and then I added 60 for arc WX, and that's because the measure of the central angle is always the same as the measure of its subtended arc. So if WX is 60, the central angle will be 60. If the central angle WVX is 60, the arc it subtends will be 60. So let's take a look. The first step, the measure of ZWY. so this is this major arc all the way across, is 360 minus the measure of YZ, which was 45. So this total arc from Y through X is 315 degrees. We also know that the measure of YXW is 180. At this point, I would probably solve and say that 180 minus 60 is 120. They're doing it a different way. You're going to find that you'll have many options to solve these circles, arcs, and all the pieces of the circles. We'll just follow along with the book, but right now I already know that XY is 120. We're also going to prove it another way. So the measure of YZ plus the measure of ZW equals the total measure of YZW. So using algebra and subtracting YZ from both sides, we can say that 180, because this was a semicircle, minus 45 equals 135. So now we have another piece. We have the measure of ZW here as 135. Let's move on. And for the last part, we're going to solve for ZX, starting to get dyslexia here. And we know that it's the measure of ZY plus YX and to solve for YX, they're saying 180 minus 60, which is what I was talking about on the last step. So I'll go ahead and write that in right now, and which is 120 degrees. And ZX will now be equal to the total of 45 plus 120, which is 165. So that should give you an idea of how we'll be working these problems. Suggestion, once again, like I always do, have a piece of paper that has all these properties for the arcs and has all the formulas with some pictures on the side, so they'll help you to solve these. A few points we want to discuss. I'd like to look at the drawing first. We have two concentric circles. Remember that concentric circles are circles that share the same center. They're on the same plane, and they both have measures of 360 degrees. The circle with the largest diameter will have the greater circumference, and this just makes sense. So, using the same drawing, in circle C, the measure of arc AB equals the measure of arc DE, which equals 60 degrees. So this is what they're giving you, that angle is 60 degrees. So the length of each arc will be 60 divided by 360, or it's a portion of the whole circle. 60 divided by 360 reduces to 1/6. So this arc for both of these circles is 1/6 of the circle's circumference. So the length of AB would be 1/6 of the circumference, which is 2 pi r, and 2 pi 6 for the smaller circle, which is 12 pi, divided by 6 is 2 pi. And for the larger circle, 2 pi, and the radius for the larger circle is 6 plus 3, which is 9. So that's 18 pi divided by 6 is 3 pi. So we've now proved that the radius will be determining the actual circumference of the circle. Our first theorem for this lesson: if an arc of a circle with a radius r and circumference of C equals 2 pi r has a degree measure of theta, an unknown number of degrees, the arc length L is given by this formula. The formula is arc length equals theta divided by 360 times the circumference. So get that into your notes. And let's use that formula. So we're going to find the value of each variable. So we have a circle with a radius of 10 yards. We have another radius that will also be 10 yards. We can see that the two radii are forming a 90-degree angle, and we'll be solving for the arc length. So we use our arc length formula. We insert the 90 into where theta was, because we now know how many degrees. We insert the length of the radius, and 2 times 10 is 20, so we'll have 20 pi here. 90 and 360 reduced equals 1/4. 20 can be divided by 4 evenly, so 20 divided by 4 is 5, and we're left with 5 pi yards, or approximately 15.7 yards. Another part of this same example, using that formula, we're now going to solve for theta. We have an arc length, we have a radius length. So we're going to insert the arc length into where we have the L in the formula. We don't know our central angle yet, so this will be theta over 360. And our formula for circumference is 2 pi r, which is 15. Now 2 times 15 is 30. Let's begin by canceling out pi on both sides, which is the same as saying we're going to divide both sides by pi. Let's reduce 30 by 5, which leaves 6. And now we have 6 theta over 360. Well, 6 and 360 can be reduced, so you'll end up with 1 over 60 theta. And if we solve for theta, we'll multiply by both sides by 60 to solve for theta, and we end up with theta equaling 60 degrees. Now we're going to find the measure of the minor arc in this problem. And all of these pieces of this example here will be used in example 3. So it's important that you label what you're solving for. So A was solving for finding the arc length. B was solving for the central angle, theta. And C is solving for the radius. So using our formula, we'll substitute the values that we know about. We have an arc length of 4. We have 30 over 360. And how did we get that 30 degrees for theta here? Well, we have a major arc length of 330. So all we have to do to find the degrees of the arc length is 360 minus 330, which is 30. And remember that the arc length, the degrees in the arc length will be the same as the central angle. So theta equals 30. So we have 4 equals 30 over 360 times 2 pi r. I began by reducing the 360 by 2, and we end up with 30 pi over 180, and then I multiplied both sides by 6 over pi, which now eliminated pi on the top, and we are left with radius equals 24 over pi, which is approximately 7.6 feet. Now example 3 takes this a little further. We're going to find the perimeter of a sector and the segment. XY. So the sector is XUY, this whole shaded piece, and the segment XY. So what they've done is a blow up of the sector below here, and this will help us find our answers. So we're going to begin by finding the arc length. So we use our arc length formula, and arc length equals 120 degrees over 360, 2 pi 12 feet, or 2 pi r. 2 times 12 is 24, so we have 24 pi. 120 over 360 reduces to 1/3. 24 can be divided by 3, which is 8, and so our arc length is 8 pi feet. So the second step, the sector's perimeter is actually the sum of the two radii and the arc length. So UX will be 12 because it is congruent to UY. So we can say 2 times 12 feet plus the arc length, which was 8 pi feet. I've used distributive property to shorten that, and 24 plus 8 pi, I used my calculator to find out the decimals for pi, added and rounded to 49.1 feet approximately. Now our third step is finding the chord length. So the chord is part of this 120 degree triangle, and one of the things we know about this triangle is its isosceles, because it has legs that are radii that are congruent to each other. So if this is 120, x and y have to add to 60, which means they're 30 degrees. So this is a 120 by 30 by 30 triangle. And if we drop an altitude from U to the chord and bisect that chord, we now have two 30, 60, 90 triangles, and we can use our ratios for 30, 60, 90 to find the piece or the long leg of both of these 90 degree triangles. So we know that we have a hypotenuse of 12, which is equal to the 2x in our ratio. So that means x will be half of 12, which is 6, and the long leg will be 6 square root of 3. So the length of the chord will be 2 times 6 square root of 3, which is 12 square root of 3. A lot of steps there. And our last piece, the segment's perimeter equals the sum of the chord and arc length. So the chord length was 12 square root of 3. The arc length was 8 pi, both of them in feet. If we use our calculators to find decimals, we have approximately 20.8 plus 25.1, which is approximately 45.9 feet for the answer. Okay, moving on to some more definitions. Congruent arcs or arcs and congruent circles are the same circle that have the same measure. Let's look at the circles. And we have circle Q and circle R. They both have central angle measures of 20 degrees and arcs that are subtended, which will also be 20 degrees. So the measure of AB is 20, the measure of arc CD is 20, and circle Q is congruent to circle R, so the arcs are congruent. This brings us to our next theorem. In congruent circles or the same circle, minor arcs are congruent if and only if the corresponding central angles are congruent. So we just did this in the last definition. So that would mean that angle P and Q, if they are congruent, then XY and UV will be congruent. And if chords of congruent circles of the same circle are congruent, if and only if they intercept congruent arcs. So if X, Y, and UV are congruent, then their chords X, Y, and UV are congruent. And note the statement down here below these circles. You can see the chords are indicated by the straight lines. The arcs are indicated by the arc symbols, and those have to be on your paperwork for us to discern which you're talking about. Next theorem, incongruent circles. Chords are congruent if and only if the corresponding central angles are congruent. So if angle P and angle Q are congruent, then chords X, Y, and UV will be congruent also. So these are all pieces of the circle with their congruency. You'll become accustomed to them. They're very intuitive, and you'll be using them quite a bit. And our last theorem for this lesson, incongruent circles. Chords are congruent if and only if the corresponding central angles are congruent. And chords X, W, and UV will be congruent if and only if the central angles are congruent. So now we've brought all those pieces together, the central angles, the chords, and the arcs. So your homework, and your homework, you have numbers 1 through 3, number 5, 7, 12, 15 through 16, 19 through 22, 25, 27, 53, and 54. We'll be covering a lot of these in class. If you have questions, please bring some notes about which questions you need help with. In the meantime, here are some hints. Numbers 5 and number 7 are the same as example 1. Number 12, insert the given values into the formula for theorem 8.3.1, which is the measure of the arc length, and solve for the radius. In number 15 and number 16, use theorem 8.3.4. In number 22, use the arc length formula to solve for arc length, then sub your answer into the formula for perimeter. Take a look at example 3, step number 2 to help you with that. Number 25, solve for the radius, then sub the answer into the perimeter as in example 3, number 2. And number 27, this is also example 3, but just a hint, the chord and the radii form an equilateral triangle. So if you need assistance with any of these problems, be sure to contact me. We'll cover them in class until we get them down pat.